A gente já tá.
Yes, we are ready. Hi, everyone, and welcome to the second section of Brazil Pore Talks. Before we begin, I'd like to introduce our new team member, Professor Thais Nascimento Pessoa from the Center of Nuclear Energy in Agriculture at USP. Welcome, Thais. Today, we have two amazing presentations. Each presenter will have 15 minutes to speak, followed by 5 minutes for a question. So please be my guest and send your questions in the YouTube chat. Let's get started. I have the pleasure of co-hosting this section together with Professor Felipe Monarim from the Federal University of Ceará. Welcome, Professor.
Welcome. Good afternoon, everyone. First of all, I would like to thank Natalia Almeida for accepting the invitation to present her work in this initiative, which we intend to disseminate and acknowledge, bring together professional working in porous medium research. Natalia, she is a multidisciplinary professional because she has a PhD in geophysics. She's doing a PhD in geophysics at the Federal University of Pará. She did her master degree in chemical engineering, and she holds a degree in petroleum exploration and production engineering. So she has knowledge in different scale. But in her research focuses on active flow in porous medium, computational modeling and simulation, computational fluid dynamics, and matrix oxidation. She works at the Laboratory of Petroleum and Energy Science and Engineering at CBPF. So, Natalia Almeida, the transmission is yours.
Thank you. I'll share my screen now.
Yes.
Let's see. You can see my presentation?
Exactly.
Yes.
Good afternoon. It's a pleasure to be here talking today. Felipe already introduced me. I'm Natalia Almeida Braga. And my work that I'll be presenting today is 3D simulation of reactive flow in carbonates with porosity fields extracted from micro-CT images. So a brief introduction of carbonate acidizing, that's the process I'm simulating. Carbonate acidizing is a type of well stimulation. It's employed in oil fields to enhance production. One of these methods is acidizing, specifically in carbonates. The acid fluid that is injected in the well, it reacts with the formation, forms high permeability channels that are called wormholes. And these channels, they promote greater flow from the reservoir to the well. In laboratory, what we have here in LC in Salinopolis, we can study the efficiency of this process with a core flooding equipment. A core flooding is an equipment to simulate reservoir conditions at a blood scale, so the scale of a carbonate sample around 6 inches in length, 1.5 inches in diameter. This sample is pressurized inside the core holder, and fluids are injected with the help of injection pump. So the fluids go from the accumulators to the core sample inside the core holder. And we can heat the system to simulate reservoir temperature too. There's pressure transducers to monitor the pressure during the whole process. And while the fluid is being injected, we see that the difference in pressure between the inlet and the outlet of the sample, it begins to fall as the acid moves through the sample and starts opening these wormholes. The resistance to the flow, it, it starts to decrease until it reaches a minimum point that we call breakthrough. It means that the wormhole went from the inlet to the outlet of the sample. And this scale is what is being simulated with my computational model. It basically represents a core flooding experiment. And these types of model, it needs initial information to initialize my model. In literature, we see a lot of methods to initialize these informations. One of the information needed is a porosity distribution to simulate the real rock porosity. We have ways to initialize a field. We, in literature, we normally see normal distributions, log normal distribution. Uniform distribution is very used too. And we can use image-based distributions that we try to employ here. An image-based distribution, it's taken from microCT. MicroCT is a form of imaging, a non-destructive image technique. It works the same as a medical X-ray. When we go to the doctor, we take an X-ray, you can see our bones, our internal structures. It's the same for a rock sample. And the micro in microCT, it means that we can see in great detail. So we can see the pores, you can see wormholes when they're formed. And these images, they can be taken as my initial information to initialize a porosity field. So we're taking information from real rocks. We have some previous results. 2D results comparing the use of uniform distribution with the image-based distribution. So we take just one image and compare how the results perform. We can see some greater deviation from a straight path when we use image-based distribution. And later we got 3D results with uniform distribution. So the idea of this work is getting these uniting these results from 2D and passing them to a 3D domain. So instead of just a single image of the rock, we get all of the images that compose the rock. We unify them, and we get a full 3D field. So the objective is incorporate real rock heterogeneity in the simulations at the plug scale. Here's a brief look at the mathematical model that's being used. We have momentum and mass conservation to solve for velocity and pressure, the transport of the acid species, a porosity evolution equation, some equations that relate to permeability, pore radius, and interfacial area, and how they will change as the porosity changes due to dissolution. We have the components for mass transfer and the dispersion tensor. And the other fields, permeability, pore radius, and interfacial area, they need to be initialized too, and they're initialized with correlations with the porosity I get from the image. Here a brief example of the domain. So we have the fluid entering at the inlet boundary, a constant pressure at the outlet, and all while the simulation is being run, we also monitor the difference in pressure from the inlet to the outlet. The methodology to get these porosity fields in 3D, we initially have a micro-CT volume. These micro-CT volumes, they come already separating in various slices. The slices are the 2D images. They are stacked to form the full volume. So we start with the first slice, and then the algorithm, it reads all of the grayscale values pixel by pixel from the image, and then with the full grayscale array that I get from that, I can calculate porosity values, and these porosity values are approximated by a sigmoid function. So it goes through this function that takes into account the grayscale value that is being measured in the pixel, and also maximum and minimum values that I choose for my curves, for my sigmoid curve. And with all these informations pixel by pixel, I need to transport these informations to cells. Usually I have much more pixels than I need for simulation. So we have here, for example, this area here that will become a cell. So all of these pixels that are inside the same area, we make a, we measure the mean of all these values in the same area, and this value turns out as the value of porosity in that cell. We do that for all of the cells. We generate a 2D porosity fields, and then the process repeats for every slice. Then with every field for every slice, I can stack them. The same principle that is used for the micro-CT, I stack all of these 2D slices to form my 3D field. Here are some of the results. I have results for Indiana limestone. The Indiana limestone is a formation known in literature for being comparatively very homogeneous. So we expect that we don't expect large porosity contrasts in the Indiana limestone samples. And when I simulate with Indiana limestone, when I extract the porosity information from Indiana limestone, I get these histograms here that are considerably close to I ended up approximating by a normal distribution, but it's also very close to a log normal distribution. And when we see here the PVBT curves, the acidizing efficiency curves dependent on the injection velocity, we see here that the image base here in yellow and the normal distribution case ends up getting very close to each other, and they also don't have some decimals of difference from the experimental curves. So for Indiana limestone system, getting an image-based porosity field or using a normal distribution, they end up being quite equivalent. But when we have a more heterogeneous system, a system that is very different from Indian limestone, like the pre-salt carbonates, here we have the porosity fields generated from pre-salt carbonates. We have here the microscale image of two samples, Al2 and Al4. We see here the internal fields generated by the algorithm, and also side-by-side comparisons of the first slice with the inlet face. Here the microcity and the one generated by the algorithm, and also correspondent normal distributions. You see that's a great difference here in how the porosity distributed. And we have some histograms here, and we see already that they don't look so much like those smooth curves we could see with the Indiana limestone. And we have some comparisons for the image-based model and the normal distribution. These simulations were run with 300,000 cells. Is the minimum amount of cells for the results to not be dependent on mesh refinement. So my mesh independence test arrived at an stabilization of the results at 300,000 cells. So we have wormhole comparisons here. At this mesh refinement, we don't see much difference with the wormholes that were formed. They are all kind of straight. We can see here some minor deviations here, but in general, the results were more in the acidizing efficiency, the PVBT. We see here for a tendency for the wormholes to start at the center of the domain. We can see here that in the center are the greater porosity values. And here with the normal distribution, we don't have a special preference for the channels to start to form. Here we have it at a greater velocity. We have some more wormholes being formed because of the greater velocity. And some here, especially if this sample here, Al2, we can see the wormholes are starting to get more rougher, more deviate more from a straight path. And we have the comparison of the PVBT curves. That's what I said about the major difference here was the acidizing efficiency. We can see that the image-based model got lower PVBT values. Here, the blue curve, we see that's consistently below the red curve that corresponds to the normal distribution. And why this happens? It's what we generally see in literature is that more heterogeneous fields promote the formation of preferential paths. And these preferential paths, they accelerate the breakthrough, they facilitate the path for the acid to flow from one side to the other. So here, I also studied the effect of mesh refinement. Like I said, all of these previous results were with 300,000 cells. So we have now results with close to 2 million cells to get the more of a visual effect. The PVBT is not affected anymore above 300 cells, but we have some visual effects. Like here we can see that especially Al2 that had more contrast in its porosity field, we can see more branching here. You can see that wormholes, they are branching more as the cell size is reduced. We get to see not only smaller scale heterogeneity, but also the process of taking the mean in each space. I end up losing some information. So as I reduce cell size, I can get more of the peer information from the pixel. And you can see here that the normal distribution nailing gives those straight wormholes, and they don't have much of a preferential spatial preference to start form. As you can see here in AL4, that they mainly start from the center of the sample. So conclusions, the porosity distribution of Indiana limestone, they approximate well with Gaussian curves and other similar distributions. Like I said, it's very similar to a log normal distribution. But the same behavior is not seen with a more heterogeneous system like the ones we see in the pre-salt carbonates. The PVBT curves from microscale images were consistently below the PVBT curves that were obtained with the normal distribution because of these preferential paths that are being more represented when you get a heterogeneous system. And the greater mesh refinement captures smaller heterogeneities, and this consequently promotes the branching of wormholes for the image-based fields. We can see more of this effect when we refine the mesh. Some acknowledgements, and thank you for listening.
Thank you. Thank you. Very nice talk, Natalia. I have just a question. After that, we can see if someone has a question. Did you said you use sigmoid function to use in the segmentation, yes?
Yes.
Do you want to change to use or to try another function just to see if it's better or not to use another function to make the segmentation?
Yes, we made some literature reviews already to see other functions that can be used. There are also some methods that that take the grayscale values more directly from segmentation from microCT that I already implemented, but I hadn't the time to really test it yet.
Yes, but you touched a lot of things here. Yes, it's very good, the presentation. Someone else has some question?
Sorry, Anderson, I opened the mic. My question is related to what Felipe has already told about the segmentation. I'm not worried, but I'm thinking about the voxel resolution. Have you tested for different size? I mean, high resolution, if your model works in a different way? I don't know. Maybe I missed something in your presentation, sorry.
It's all right. These samples here, usually I get what we already have, the image we already have. All of these same Indiana limestone samples here, some of them I know are at around 42 micrometers, and some of
Okay.
them are around 20, 24 micrometers. So some of those, they are different voxel sizes.
Yeah, because this could influence in your, how is the name of the gray?
The grayscale reading.
Yes,
Grayscale.
exactly. The grace, yeah. So yeah, but it's okay. I understand. You have to work what we have in hands, no? Sometimes.
Usually, we never use the full number of pixels, so information always gets lost when we transform some pixels to cells. We take the mean, so I can't assure you how much is lost because of voxel size.
Okay. Okay, Anderson.
Okay, thank you. Hi, Natalia. Very nice work, very nice presentation, nice talk. Congratulations. And I'm an experimentalist. So I would like to ask you something not related to the experiment itself, but the application of this in field. So in field, we have the reservoir rocks, and they are sealed by cap rocks. How do you control that to prevent that this acidification don't pass to the cap rocks in order to prevent the oil to spill into the sea and something like that? Do you know something about that?
I'm not much of a field engineer, so I can't. I mean, I can't say something I'm not sure how to answer.
But the acid is the same for any kind of rock, or do you have a specific acid for a specific kind of rock?
It really depends on the project. It depends on the rock, the pressures that are being used. Some rocks are harder, some rocks are softer. So depends on the season and how we want the progress of how we want the operation to progress. There's a lot of acid formulations. There's straight hydrochloric acid there. We can use additives. We can use organic acids. It's a whole world of different formulations.
Thank you.
Pedro, if you wish to compliment Natalia, please feel free to talk before me. I'm not sure if you want to just compliment.
Yeah. Thank you, Diego. Can you hear me well?
Yes.
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 The Anderson, the main idea of the acid treatment is treat the reservoir. So we inject the acid and in the reservoir. In really, we have difficult to put the acid in the lower permeability regions. So the acids flows to the in the reservoir part, and different from what we have in, for example, in CO2 injection, that the CO2 reacts with the brine and form carbonic acid. It's a very slowly reaction. We inject HCl, and when reacting with carbonates very strongly, very rapidly, so have not time to arrive in the cap rock. So normally spend it in the during the injection, quickly spend it in the rock formation. So really we are worried to try to retard sometimes the reaction to improve the performance of the acid penetration, the wormhole propagation. So it's a different concept regarding just to clarify this question.
Thank you, Professor. Thank you.
Okay, I think that I may continue the questions. First of all, Natalia, congratulations. It is a really great work, really nice, really interesting. And I'm really happy to see you again and presenting all this cool stuff that you guys have been working on. I have actually a dumb question. I was curious about you have a simplified case where you set a distribution to the porous medium, and then you have an equivalent porous medium to compare against images. I was wondering, how do you set the distribution parameters, like the mean or the standard deviation? Where you get those information, this information to put in the porous media generation? Just curious from my side. Thank you.
Okay. We can see here. Generally, like I'm working with normal distribution to compare. I use the same mean as I get from the image-based model. Usually, I actually tune the image model to match this computational mean with the experimentally measured mean for the sample. So I always match them, and the same for the normal distribution. It's all the same mean for the real sample. And the standard deviation, I usually use around 10% of the mean. It's just like, I'd say a standard value. I can for sure use a greater standard deviation or a smaller standard deviation. I just keep it around 10%.
Oh yeah, nice. It's just a curiosity question, because I also have some codes that are doing something similar compared with what you are doing here, but with the real images like you are doing. But I was curious because if I get you right, you get the porosity mapping from the image using the sigmoid function, and then you compute the statistics, right? And then with the statistics, you can parameterize distributions like the normal distribution, and you can generate. It's something like this.
Yes.
Is this correct? Yeah.
Yes, I always try to see all the image statistics to get as close to the experimental values I have for that sample.
Oh, I see. Really interesting. The results actually are are really close. I mean, maybe we don't need this level of details from the images if we have
Yes.
it of course depends on the anisotropy of the image. Of course, I think that if you have a heterogeneous image, I think that as you have shown, we may struggle with this kind of statistical approach. I think really
Yes.
nice. Thank you. Thank you.
Sorry, guys, I think we have to move on. A lot of questions to Natalia, and maybe we can send by email. What do you think, guys? Sorry, Ingrid, next time.
My mail is right here if you want to contact me.
Perfect.
Great presentation, Natalia. Thank you very much.
Thank you.
So, just a quick reminder before we move on to the next talk, don't forget to follow us on our social media channels and to stay updated, okay? And if you have any question, please leave them in the YouTube chat. Rodrigo, please, if you can share your screen while I'm introduce you. So let's continue with Dr. Rodrigo Carlos Viana Coelho. He is an associate researcher at Brazilian Center for Research in Physics, with more than 10 years of experience applying the Lattice-Boltzmann method to study a wide range of fluid systems. His research spans electron hydrodynamics, liquid crystals, active matter, multi-components flows, and transport in porous media. He holds he holds a PhD, a master degree in a background in physics from the Federal University of Rio de Janeiro, with part of his doctoral work accomplished at ETH Zurich. He was a postdoc research at the University of Lisbon in Portugal, and has also worked in industry, including a research internship at ABM, Research Brazil, and the position as a development engineer at Numeca International in Belgium. So welcome, Rodrigo. The floor is yours, or the transmission is yours.
Okay, thank you very much, Yara, for the introduction. Okay, and I'd like to thank the organization for the invitation and for letting me present this work, and congratulate for this amazing initiative. I think it's something needed for our community in Brazil, and not only. Okay, so I wanted to present something different from what I have shown in the previous Interpore in Santa Catarina. So the talk is in a completely different topic, but it is related to porous media, as I will show. So it might look a bit exotic for you, but it is related to microfluidics and porous media. Okay, so active fluids, that is the kind of fluid that you treat, is a kind of system in which the particles, they are self-propelled. So a classical example is a colony of bacteria, in which each bacteria can swim. And if they are densely packed, they have this collective motion that is very different from the individual motion. So they behave, if you extract the velocity field, it looks very much like fluid turbulence. But the difference is that it occurs for micrometers, so for small length scales. So the Reynolds number here is very small. So just to give you some idea of the different effects that occurs for active fluids, you are probably used to the Saffman-Taylor instability that occurs when you try to extract oil by injecting water that is much less viscous. But if you inject one fluid and try to displace another with the same viscosity, usually, well, you don't have this instability, this finger instability. Something different occurs when you inject a fluid with bacteria, for instance. This was found experimentally in this study. Is from the last year. It was a PRL. So they inject a fluid with bacteria to displace another one with the same viscosity and the same properties. And if the concentration of bacteria is above a certain threshold, they do observe the viscous fingering. So the Safman-Taylor instability occurs for fluids with the same viscosity, the same fluid viscosity. But, well, they have explained this behavior by measuring the effective viscosity, and they observe that it decreases with the concentration until it reaches zero. So the effective fluid viscosity becomes effectively zero, like a superfluid. So it means that the bacteria are swimming all together in the direction of the imposed flow, which is very nice. Another effect is occurs when you impose a pressure difference in an active fluid which is passing through a porous medium. So again, the active fluid swims in the direction of the imposed flow, and you always have a velocity which is higher than that obtained for a passive fluid. So they call this an active Darcy law, and even derived some equations for this. So two recent observations for active fluids, and this one is directly related to porous medium, the active Darcy law. Okay, and the kind of active fluid that I study is called active nematics. It is also composed of active particles, like bacteria which are swimming, but they try to align with the neighbors. So those bacteria, so if you are dealing with bacteria, they are elongated and densely packed so that they align with the neighbors, as you can observe this. So columns of bacteria is one example of active nematics. Another example is a mixture of microtubule and kinesin. So those are components of that we can find inside the cells. The microtubule, they give the rigidity of the cells, they give the shape of the red blood cells, for instance, and also form the flagella of the bacteria, while the kinesin are micromotors that transport organelles from one side to the other, using the microtubule as a guide. So someone had the cool idea of putting those two components together in an oil-water interface. So you have the oil on the bottom because it's heavier, you have water in the top, and you mix everything in the beginning, and then they deplete to this interface and form an effectively 2D system. And because they are densely packed and they are active, they form this kind of flow, which again resembles fluid turbulence, but occurs for a small Reynolds number. So you can see topological defects, like they are comet-like, going in all the directions here, and can also find some negative defects. So the dynamics here is controlled by topological defects that occurs in the liquid crystals. So a question that arises, well, you have this chaotic flow. Can we control it to extract some work from it, some useful work? So maybe we can direct this flow and produce some pumps. That's the topic of this talk. Or you can also achieve persistent rotation or propulsion. So that's the question that I will try to address, mainly this first one, how to achieve directed flow. And I will focus in this kind of system, the mixture of microtubule kinesin, because I have a collaboration with a group in Barcelona that they are expert in this kind of system. So I will compare with their experiments. Okay. Well, since this system is already well known, it's reproducible, it's cheap to produce, it's biocompatible because all the components are extracted from the cells. People are thinking if you can produce some applications for it, some microfluidic applications. For instance, in this work, which is not so old as well, 2 years ago, they proposed a micromotor. So if you use a colloid which has this chiral shape, it rotates in a certain direction, and this rotation is persistent. So this could be used as an ingredient for a micromotor. Again, remember that we are in a 2D system, so in the oil-water interface. Well, in many applications for in microfluidics, you might need pumps. So how to pump fluids into deep? That's one question, because we usually use hot rotors or external forces, which will pump all the two fluids, including the interface. So how to pump only the fluid which is at this interface? That's one question that we will address. And another one, well, can you use the energy of the fluid itself? Because it's already moving, so it has internal energy. So maybe we can extract this energy and direct it to produce pumping. Okay. I did this the simulation part. So I used a continuum model. It means that we are not simulating the individual particles. So we are simulating a mean field theory. Those particles, they interact with the flow field, so they can change their orientation depending on the velocity gradient. We have an energy penalization for distortions in this directed flow. And more importantly, we have an active stress, which adds the energy to the system. So this is what causes the internal motion, the internal energy. And just to give you a little bit of details of, I'll not give all the details, but just the equations. So we solved the Beres-Edwards equation, which is an equation for the directions of those particles. So it gives the time evolution of them. And we also solved the Navier-Stokes equation with this active stress. So those two equations, they are coupled. And one I solved with finite difference and the other one with lattice Boltzmann. Okay, and my collaborators there in Barcelona, they developed a technique in which they can photopolymerize this active fluid. So they shed light insert a region with any shape, and that region becomes solid-like. So it can become more rigid or more flexible depending on the monomers and also on the light. And it's interesting that you can produce obstacles in situ. So imagine that you are producing some microfluidic application, you can change the circuit with time. So that's a very nice technique. So what you can do with this? We started thinking, well, the simplest idea that we could have is to direct the flow. So using simulations, I tried some geometries and verified that if you have a squared lattice of triangles, the fluid goes to the right. So it goes in a certain prescribed direction. So we are simulating here this liquid crystal, these active nematics. And yeah, they have checked using their technique. So initially they have the active turbulence here. So this is a chaotic flow. And then they print those triangles in the system. And then they observe that the flow indeed goes to the right. So note that they print pillars, and those pillars, they are attached to the bottom of the system. So what we are seeing here is just a cross section, right? Because it's a 2D system. Okay, and so here we are comparing the experiments with the simulations. It's just one moment, one instant of for the directed field. And here we see the average velocity field. So it's a time average. And you can observe that they both are quite similar. And they exhibit those red spots between the obstacles, the triangles, which are present both in the experiment and simulations. And we can also observe an interesting feature that are those vortices here. So behind each obstacle, you have two vortices that you can observe clearly in the vorticity field. So we believe that those vortices, they are also helping to guide the fluid to the right. So this creates a pumping mechanism that we can use in applications. We have characterized this system using simulations because first we have made many tests and characterized the system to give to the experimentalists to not spend money without profit. And for instance, we have fixed the cell size and changed the triangle size, and we see that initially the flow rate or the velocity field increases as the triangle site increases, and then it reaches a maximum. Later it decreases more slowly. So this maximum is related to the characteristic length of the active fluid. So this is something that is known in the literature. It's a competition between the elastic energy and the activity that produce a characteristic length for this kind of fluid. So this could be measured, for instance, by calculating the average size of the vortex or the average distance between the facts. So it's interesting that the maximum occurs exactly for this length. And we also changed the cell size and found the optimal configuration. So we gave this to the experimentalist to do the test that we see. Okay, and since we are talking about pumping, we can compare this with a combination of pumps, of hydraulic pumps. So there are laws for ideal pumps in series and parallel. For instance, when they are in series, you would expect that the flow rate is constant and the pressure difference increases with the number of pumps. So we can do some analogy. So we take one pump as being this unit cell. And here we see the velocity field across the system for just different number of triangles, of pumps. And we see that there are those peaks that are related to those red spots that we have seen before in the average velocity. And they stabilize after a certain number of triangles that you can see here. We can also plot the pressure difference across, or the pressure across the system. So what we did was to plot the pressure difference across the system, so in the beginning and the end, and the velocity at the end against the number of triangles. So with this, we can compare with the behavior for ideal pumps. So initially, the flow rate or the velocity increases with the number of pumps, which is a non-ideal behavior, and later it stabilizes. So here, after 10, more or less, 10 triangles, we have the behavior of something close to the behavior of ideal pumps, while the pressure difference increases almost linearly with the number of pumps. This is closer to the ideal behavior. Oh, we can also do this for pumps in parallel. So we increase the number of rows here. And well, the flow rate increases with the number of rows, while the pressure difference is almost constant. So in this case, the behavior is closer to the ideal one. So it's interesting that this system, this active system, follows more or less the rules for hydraulic ideal pumps for a certain number of triangles. Okay, and if you have pumps, we would like to pump fluid in other geometries, like in a porous medium or in a channel, or, well, so here we coupled the triangles with a squared lattice of circles, which is a isotropical configuration. And we see that the velocity field does penetrate until a certain length. So the pumping mechanism is working until a certain length. Later it dissipates because the system is open, and also because the fluid is active, so it tends to dissipate the energy later. But the pumping is working. And also you could think in more complicated microfluidic circuits, like when you have curves, for instance. So we don't need to have only pumping in one direction. And if you follow the traces here, you see that they are more or less following the prescribed direction given by these circular trajectories, like a big vortex, which was confirmed in experiments. So you're not seeing here the traces, but can believe me, they have tested. Well, guiding the flow is interesting. You can use in applications. But another possible application is in micromixing, because it's well known that it's difficult to mix fluids in the Stokes regime or for a small Reynolds number. For instance, in this experiment that probably you have seen before, when you try to mix the droplets, of different colors in a very viscous fluid like glycerin, you can rotate the cylinder, which is the inner cylinder in one direction, but when you revert the motion, you see that the three droplets, they are not really mixed, so they come back to the original position, so the initial configuration. So so it's difficult to mix fluids for a small Reynolds number. This is a challenge in microfluidics. So can the active fluid help on that? So we have tested to mix two droplets in isotropical configuration, isotropic lattice of circles. And we observed that the droplets do mix, but the center of mass remains almost fixed in space. Well, and when we try with a lattice of triangles, the droplets also mix because there is transversal flows in the perpendicular direction to the mainstream, but you have these downstream. So this would be very interesting in applications because you don't want to mix only two droplets. You want to inject fluid, two fluids on one side, and recover the mixed fluid on the other side. So this kind of setup would be good for this kind of applications. For instance, involving pharmaceuticals, solids. Okay, so this is what we had to show about the triangles, but just to advertise some further works that we have worked. We have also investigated the dynamics of capsules in active nematics. And well, for instance, a summary is that we observed that they can achieve persistent rotation and also and also propulsion, depending on the conditions. Well, here we only see a circular flexible capsule, but depending on the conditions, they do rotate and they do have propulsion. And another study was that we investigated what happens to the active nematics in contact with a passive liquid crystal in the symmetric phase. So the symmetric phase has an easy flow direction with which order the flow. Is a beautiful experiment that you where we observe the self-organization of the flow, and we also observed some spatial temporal patterns that emerge. So if you are interested, you can check in those publications. So to conclude, we have investigated both in simulations and in using experiment that a squared lattice of triangles could direct the flow, and this could be used as a pumping mechanism to guide the flow. And this could also be used to micromixing. So if you want to know more, I have those reference. I would like to thank my collaborators from the University of Barcelona that did the experiments. And well, if I may, I would like also to take the last minute to advertise the conference that we are organizing in Rio de Janeiro, the 9th Brazil Interpore chapter, which will be in August. Well, the deadline has closed, but if you haven't submitted your abstract, you are lucky because we have extended our deadline to July. So, you will be very welcome in Rio de Janeiro, and we are preparing an amazing conference. I hope it will be very good. So, thank you for your attention.
Thank you, Rodrigo. A very nice presentation. Really nice. I must admit, this is outside of my expertise, but I really appreciate your talk. Wonderful to hear about the Brazil Interpore chapter event. And for those in the audience, if you haven't submitted your work yet, there is still time, as Rodrigo pointed out.
That's it.
So, yes, thank you. Felipe, you have a question?
Yes. First of all, it would be very nice to meet everyone in the Interpore Brazil chapter. Well, Rodrigo, it was very nice presentation. Very interesting. Well, I work with something similar at the past. I have some technical question, but actually you showed that I'm asking about active particle. You showed in the last move that you put some object inside. It's not particle, yes?
It is a capsule, so it has also active fluid inside. So
Yes.
you could fill this with solid as well, but our contribution was to analyze what happens when you have active fluid inside and outside. So this would produce some different results because the fluid which is inside can also produce some rotation. So depending on the if you have a circular capsule with a specific size, you achieve two defects, which keeps rotating and the rotation is persistent, and this rotation produces rotation in the capsule as well. So this could also be used as a micromotor.
Yes, exactly. And do you think that put some obstacle, some points, yes, obstacle like a triangle, or like you should, this particle can be tapped there or dropped or stay stuck in this obstacle, or
Yeah, that's a very good question and a suggestion as well. We have not investigated this, but well, probably yeah, it's an open problem. Probably it depends a lot on the flexibility, and we didn't do this, but we could achieve some non-trivial results. Like
Yes.
they might be better to pass through a lattice of obstacle, for instance, if you have active fluid inside. But that's something we didn't work yet. But thank you for the suggestion.
Very nice, very nice. I think Anderson has a question.
Okay. Rodrigo, very nice talk. Thank you for the presentation. Thank you for extending the deadline of the Interpore. And Rodrigo, this is a auto-propelled fluid. We can see that. So
Yeah.
you can disturb things that are not disturbed, you know. And you mentioned different applications of this technique, but my question is more a curiosity. Do you think that this technique can be applied to enhanced oil recovery to try to get more oil from the rocks, the porous media of rocks?
Yeah. Thank you for this question. It's a pertinent question. Well, something. Well, let's see. If you think on this, the first slide that I have shown this about the analogy with porous medium, where I mentioned the active Darcy's law and also the Safman-Taylor. Well, the active particles, they tend to decrease the viscosity, which is usually not good for if you want to displace fluids. So if you are injecting water with some active particles or bacteria, it would leave more oil behind, which is not good. But well, maybe in some regime, this kind of effect could help, because if you impose a flow, the bacteria or the particles, they tend to swim in the direction of the prescribed, the imposed flow. So maybe after extracting the fluid, this effect could help. But it's something that I'm just exercising. But I have no idea actually. But
because the oil is there, is trapped, and if you can somehow to move that oil, to take that oil out of the trap, and then you go with the flow again. Perhaps
Exactly.
it can be a step for the EOR.
Yeah. But, very nice comments.
Let's work on that.
Yeah, let's see.
Thank you.
We can discuss.
Okay, Munarin, thank you.
Thank you.
Yes, just a very quick question in the direction from Anderson's question. You showed that you can mix the fluids, but you can make the opposite, the filter, like a filter, right? Separate mixed fluid, because it should be. I think it's possible, but I don't know. Looks nice to be to work as a filter also.
Well, let's see. Well, mixing is more difficult at the micro scale, but maybe if you have not a solid, but colloid, something that do interact with the fluid. This is something we didn't investigate, but maybe they try to self-assemble something closer to this capsule. If you put many capsules, maybe they tend to aggregate. And actually, this effect is real. If you have an active fluid in contact with a wall or a particle, it does produce an active pressure. So if you put many together, maybe they try to self-assembly. But the mixing, I mean, depending on the purpose, maybe it could happen. That's something that we can investigate. Maybe colloids with different sizes or different aggregation proportions. I don't know, but many ideas for further work.
Thank you, Rodrigo. Thank you. Very nice talk. Very nice talk.
Yes, indeed. I think you have to end up our session because we are already past a few minutes, but it was really nice. It's really fascinating to see you, Rodrigo. How do you jump between different areas, and was very different from your talk from here, the Interpore chapter here.
It was about coffee.
Yes, exactly. But it's amazing also. So let's thank again all the speakers, Natalia and Rodrigo. Thank you very much. And don't forget to follow us on our social media channels to stay updated with future sessions and news from the Brazil Pore Talk. Bye, everyone, and see you at the next talk.
Thank you, Natalia. Thank you, Rodrigo. Bye-bye.
Thank
Bye-bye.
you, Natalia.
See you, everyone.
Bye. See you.
Everyone.